You know what this is? This is the world's highest walkway. And this is about more than 700 feet above the floor here, way down below. And it needed about more than 1,000,000 pounds of steel. And this is a welded structure. And from this point to that point, it's about 70 feet, that large. Do you want to walk on this walkway? You know, if you do, you are trusting your life to welding and to steel. So, would you bet your life on steel welds? If you think of welding, it's a construction technique. Smoke, sparks flying, but that was yesterday's welding. Today's welding is very different. And I want to show a few slides that tell you why you should consider welding science as a mainstream material science. Today, it's the very basis of 3D printing. Every new material that is produced by 3D printing that could not be produced before is based on the science of fusion welding. The old idea about the fusion welding is really old. And welding science is really the future of manufacturing. Allow me to give a few examples. The basis is controlled phase transformations, thermodynamics, kinetics. These are the basics of what we do in material science. The old idea about welding is really that. It has no resemblance to what it is today. In the last 40, 50 years, many people from Penn State has made a difference, and thanks to their works, we have learned a lot of things that are actually powering the modern 3D printing and modern manufacturing. What I seek to do with my few slides, 4 things. I want to give you some examples of welding science and what's its role in 3D printing. But for fusion welding, there would be no 3D printing, and there would be no future manufacturing as we plan it today. And the problem with that is that any successful project of welding or 3D printing often has one goal: make better things, but increase consumption. We need more materials. And what materials do we need? I will show you. We need more critical materials. I don't decide what is critical materials. Geological Survey does. So I'm going to show you some data about where we are headed and what we are leaving for all of you to do. All right? So that's the pressure on the metal supply chain. And then give my opinion. These are just opinion. These are not backed up by very solid facts of where we may be able to do if we consider our personal responsibility for doing research. It's not just for getting something bigger and better and more clarity about complex things. It's also about our responsibility and where we fit in. So this doesn't go. If you solve a few 100 billion equations. You can then tell where the liquid metal goes inside the fusion welded zone. And why am I showing this to you? I think when you can express something in numbers, you know something about it. How do I show that? I'm going to show that with a few examples. All right? This is showing you where the liquid metal is going, where the heat is being transported. And Amrita, every cell satisfies the law of conservation of mass, because we solve Navier-Stokes equation and law of conservation of mass in every little cell, and we check the residuals for each cell. So this is different from machine learning. This is exact solutions, and the extent of accuracy you can specify in that. Yeah? So what's the purpose of doing something like that? Solving a few billion equations? You know, if you section welds, you don't always get a hemisphere like this stuff. And how do you figure out whether this is going to be a W or a bracket or a spike like this or something very different? It's again, you solve those few 100 billion equations, and the codes were written by Penn State students here, and they have made a difference in the entire field. And it's because of their works that we enjoy a lot of insight that would not have been possible without their work. So plot this, the different shapes, as a function of two non-dimensional numbers, surface tension force to viscous force that we call Marangoni number, and viscous diffusion rate to thermal diffusion rate that we call Prandtl number. And if you plot Prandtl number and the Marangoni number, you can almost predict what type of a shape this would be. What's the purpose of doing all that? What's there in the geometry is just the starting point. Okay? You need to know your domain of where you are doing your calculations or measurements. So this allows you to do just that. So these two numbers can predict the shape of the wavy weld pool boundary. Normally, if you look at Sir Badeshia's previous work, a lot of it has to do with phase transformations. And many of his books are dedicated to phase transformations. So metallurgists are used to phase transformations. And what did they do? They would take a sample, they would put it in a furnace for a given time, take it out, section it, go to a microscope, and figure out what are the phases contained quantitatively, and then try to make some diagrams that are helpful for engineers. That's what we used to do to prepare some of the pictures Professor Palmer showed, time temperature transformation diagrams or continuous cooling transformation diagrams. That's what we did traditionally. Here comes welders, and what do? They make a little homemade gadget and take it to the synchrotron center in Stanford. And I'm going to show you that picture. But let me first tell you why. Let's take a very simple case that we can all understand. 1005 steel, right? Very small amount of carbon, not many other alloying elements. So you take that, and this is the composition, 0.05 weight% carbon, and you follow this line. Here you have alpha plus gamma, and if you heat it above this temperature, you have gamma. So if you want to look at the phase transformations in this particular steel, you have alpha to gamma transformation during heating, gamma grain growth, gamma to alpha transformation during cooling. So it's a very simple system. Yeah, the phase diagram is simple. It's not very many alloying elements. So you should be able to figure out the time temperature transformation diagram and continuous cooling transformation diagrams using welding. So this is the goal: quantitatively understand the kinetics of alpha to gamma transformation both ways. Yeah, that's our goal. So what do? We make a homemade gadget in which there is a rod, and this rod can turn. There is a gas tungsten arc welder. So this is the fusion zone. And you take the synchrotron X-ray beam that is much, much stronger than what we get in the dentist's office. It goes from here, and the diffraction pattern is recorded here. Now, I am taking this picture from a paper by Professor Palmer and Professor Zhang. And what I didn't tell, Professor Suresh Babu, who is here, one of Harry's students, had a computer program in his Apple computer that he could put with the output of this photodiode array, and his program could display what are the phases with real time. Did I get that right? So he used to go sometimes late in the evening to synchrotron center in Stanford and spend the night doing these experiments, come back, and what would they get? They would get a profile like this. Yeah? So you take the solution of 10 billion equations to get the temperature time data, and you get from Suresh Babu's computer the phases as a function of time, and you have changed the field of metallurgy. Gone are the days when people used to put samples in a furnace, take it out, and you try your strength of your hand to polish it and figure out. This is what welders have done. They said, we don't need any of that. We need Suresh's computer, we need Todd Palmer to do the experiments, and we need Professor Zhang, who is still a professor at Ohio State, and you can get the entire profile. And what's the point? If you want a diagram like this that has the effect of time, that has the effect of temperature and phase transformations, so you can get a time temperature transformation diagram or similar diagrams in a matter of an hour. Yeah? So gone are the days before the welders started doing research, when the metallurgists were involved, and they would all go to TMS meeting, and there would be very heated discussions about all kinds of things that I didn't understand many times. Professor Howell and many other Penn Staters. So the point is, welding's precision and control of phase transformations are going to help us to build parts layer by layer. Yeah, that's the idea. So my point here is that gone are the days when welding was defined by the smoke and the sparks. This welding today is something that powers 3D printing. But for fusion welding and its science, there won't be 3D printing. So that's the point I'm trying to make. And what difference does it make? You know, General Electric has a plant in Alabama Huntsville, Alabama. And they make this part. This is a fuel nozzle, and the plant operates 24 hours. It makes this part, and this is special. Before 3D printing, it used to be made by assembling 20 separate parts. Today, our jet flights are safer. Our jet flights are safer because General Electric is one of the largest manufacturers of aero engines. And they make their components, many components, using 3D printing. That is why it's making a difference. What I have here on the right is the commander of the International Space Station. They needed a range in the middle of the space station, and there was no resupply mission planned. So how can NASA give them a spanner that they need very badly, but there is no resupply mission? You know what they did? Houston, we have a problem. You know what that was, right? So Houston, we have a smaller problem. We don't have a big problem. Please send us this spanner. So what Houston did, they sent a few scripts, algorithms, computer programs, electronically. And that electronic algorithm provided a machine, desktop 3D printing machine to prepare this. No resupply mission needed. So it's making a difference. This is all printed layer by layer using the principles of fusion welding. It's fair to say that welding science powers 3D printing and the future of manufacturing. So this is a very complex subject, and sometimes you need to do complex calculations, both mechanistic calculations as well as calculations that may have other names, many other names, machine learning, deep learning, statistical stuff, and so on. So I'm trying to show you what Penn State students are doing. They can tell you about the relation between process and geometry, temperature field, and features of microstructure. And that is the hallmark of material science, the connection between process, structure, properties, and performance. And today, we can do that. And we can do that because of prior research in fusion welding. We can make parts better, crack susceptibility index data. You would say, this is machine learning. Well, I say this is statistics. This is plain and simple regression analysis. Call it by any name, it is still the same, right? In MRS Bulletin, they had a news item. And I looked at that, and it has our name on it. What did you do? We have never published anything in MRS Bulletin. Well, they took this paper and they said, this is something you can do with smaller data set. Machine learning requires the quality and volume of the data to be tested before you use them for machine learning, right? But then mechanistic models can generate some of those data. They are so reliable. And we did not tell the MRS Bulletin to feature our work. They published it, and we figured out by reading MRS Bulletin that they are doing that. Okay. In short, I'm not going to discuss these results for too long, but if you are interested, we have 3 papers in Progress in Material Science recently. Total volume maybe 450 pages of additive manufacturing, single-spaced. And so there are many things that Penn State students have contributed in that area. I was invited by the US Department of State to address the diplomats, over 100 diplomats. Our task was to answer a fixed set of questions on additive manufacturing. There were 3 people who were interested in metals, in materials that are polymeric, and composite materials. And the idea there was to tell us about where the field is going and should there be any legislation to protect American interests. When I looked at the data, I saw that there was quite a bit of diversity in the applications. But if you look at the growth curve, which is what concerns many of us, because more consumption does not solve the world's problem always. Okay? It does improve the standard of living. I would like the medical implants and many other things, but all problems cannot be solved by making more. Yeah? So I want to show you something that I'm concerned with. This is not growing. You may think that additive manufacturing is the future and this and that. You look at the general consumption level for all of these things, they are not growing that much. Yeah? You know what is growing? Guess what is growing? I'm going to show you a picture. One of the problems, what I have in mind is where will all these metals come from? And look at this picture. What's happening in Ukraine? What's happening in the Middle East? Where are all these unattended, aerial vehicles and drones and similar stuff? Who is making them? Do you know how they are made? They are all made by 3D printing. This is where the growth is. And you can't figure that out by reading Web of Science. Maybe Todd will have some data, but I'm not going to ask him. Yeah. This is where the growth is. And what do we need? Titanium, magnesium, scandium they are the structural backbones of the drones. And are we sure that we are going to have all of those things for the next 20, 30, 40 years? What about our green energy ambition? Are we going to have all the metals we need to satisfy our needs? That question will come to you. That question will come to all of you to solve, whether you like it or not. You don't have a choice. So I want to show you the prices of metals that we use, ranging from less than $1 a pound to about $100,000 a pound. Yeah, quite a bit. And why is this so much diversity in the price? It's because some things are easier to get, other things are not. Yeah? So where is the problem here? These color-coded stuff are for different purpose. And we may think we want to make this battery, we want to make this solar cell, we want to make this wind turbine. What do we need to make those? That's the next question that you all have to face. So look at this. If you take today's known reserves of metallic materials and look at the consumption rate today, yeah, tomorrow it can change. Tomorrow the supply may also change because we may discover because of exploration geography. But today, some of the stuff are pretty precarious. They won't last for 2 or 3 decades. And what do you do? Do you ignore them? Do you go on exploring them? Do you increase consumption? I'm not asking you to temper your ambitions. Your ambitions for green energy is absolutely right. But then you have to go a step further. That is what I'm asking you. Ask yourself, what do you need to achieve your ambitions? And if you look for that, it's not a very comfortable situation. In fact, if you are interested in metals, then remember, production of most metals are devastatingly polluting. You make a ton of steel, you also produce 1.8 tons of carbon dioxide. Based on what we make here, this is the global production of steel from 2000 to 2023. This green one is the production of steel. It's roughly constant. If I was writing a paper, I won't produce that figure, but simply write a line. But this helps me to make my point. We are producing, on an average, about 3.6 million tons of CO2. It's for all of you to solve that problem. Because we are increasing the temperature, global warming is a fact. Yeah, global warming is a fact. And this is something that you all have to deal with. Our demands are going up for all critical metals. Why is that? Population is growing. We have ambitions of green energy and many other ambitions that require all these metallic resources. And resources are finite, and the demand is growing. Yeah? And we have this problem of emission. So the question is, how should the next generation of engineers balance all these problems with whatever? It's your stewardship. So I have a few opinions of what you should consider. I think Todd talked about put a little bit of microalloying addition to plain vanilla carbon manganese steel, which you normally call A36 steel. And if you put a small amount of other elements, the toughness will go up, the strength will go up, and you may be able to make the same structure using less steel. So it's not new discovery, it's not new research, it's existing material with knowledge of metallurgy. And the knowledge of metallurgy is in short supply globally. That is the problem. So if you had people who are knowledgeable about metallurgy, there would be legislation to bar many of the constructions using carbon manganese steel. We made that huge big building to replace the towers in New York that were bombed, right? Do you know how much steel was needed there? Do you know how much steel is needed to suspend the George Washington Bridge? It is suspended by 4 cables, right? You know how many days it took for the steel companies to make so much steel? 3-4 days. 3-4 days. So the scale is huge. So the problem you are inheriting is huge, humongous. much more than what you may be thinking initially. So if you swap materials, use the right metals based on the knowledge of metallurgy, you may be able to solve some of these problems. Using green technology is like apple pie and motherhood. Okay, it's good to hear, but sometimes these things take time. Adopting green technologies, like there was a question about the blast furnaces spitting out a lot of CO2, and what do you do about it? Well, there are solutions, but the solutions are not free. So are you prepared to pay more for steel? Steel is cheaper than bottled water and soda. Plain vanilla steel is so inexpensive. So you cannot say, clean everything up and somebody else will pay for it. You know, it's all done by China. Yeah, it's done by China, but it's also me. It's also me, because I want things to be cheaper. I don't want to pay for cleaner stuff every day. That's our problem. So basically what I'm saying is that the science of welding has enabled modern manufacturing. It's no longer the old welding. It's very different. And scientific and technological advancements, you are getting your PhDs, and there is obviously a sense of personal achievement, but with achievement comes responsibility. And my message to you is that be conscious of that responsibility. Certain things we have not been able to do, the whole world is looking up to you. And with every personal achievement and scientific and technological advancements, if you don't think of the people, there is a big hole. It's all about helping people. And all these billion equations, not going to help people. I think we need to take responsibility, and we need to take some of the problems that are evolving because of our work. And breakthroughs need to address finite reserves, rising demands, and emissions to ensure sustainable progress. All your breakthroughs and other things must benefit real people. Think about it. And thank you so much.